All right, let's get right into it. We are going to break down the three fundamental rules that basically run our entire universe. Seriously, we're talking about everything from a baseball flying through the air to planets circling the sun. These are Newton's laws of motion, and they are the invisible rule book for everything that moves. I mean, really think about it for a second. You give a box a good shove, right? It slides, and then it stops. You roll a ball. It goes for a bit, and then it stops. Why? Why does everything seem to just run out of gas? This one simple question was a real head-scratcher for thinkers for thousands of years. And it kind of makes sense, doesn't it? If you want to move something, you've got to push it. The moment you stop pushing, it stops moving. So for the longest time, everyone just figured, well, the universe must just prefer things to be still. That was the default setting. But here's the kicker. That incredibly intuitive idea is just plain wrong. So the guy who first started poking holes in this old idea was the legendary Italian scientist Galileo. He wasn't content to just accept what everyone else believed. He had a much more powerful tool, his own imagination, and something we call a thought experiment. Okay, so picture what Galileo was thinking. He imagined a marble on a ramp. Easy enough. If it rolls down the ramp, gravity makes it speed up. Obviously, if you then have it roll up another ramp, it slows down. Still with me? So then he asked the genius question, what if there is no up? What if the surface is perfectly, completely flat? Well, with nothing to slow it down, he realized it would just keep going and going forever. And this was a total game changer. The reason things stop in our world isn't because they're supposed to. It's because of this invisible force we all know and love, friction. Galileo figured out that motion itself could be a natural state, just as long as no other forces are messing with it. So Galileo basically planted the seed. A few decades later, this guy named Isaac Newton came along, took that brilliant idea, and turned it into the very first official law of motion. This is where the rules of our universe really start getting written down. Okay, I know, that sounds super formal and a little wordy, but all it's really saying is that objects are, well, they're stubborn. If an object is just sitting there, it wants to keep sitting there. If it's already moving, it wants to keep moving in a straight line at the same speed. The only thing that can change its mind is an outside force, a push or a pull. And this stubbornness has a name, inertia. So what exactly is inertia? You can honestly think of it as physical laziness. Objects just want to keep doing whatever they're already doing. They resist change. An object at rest wants to stay at rest, and an object in motion, you guessed it, wants to stay in motion. And trust me, this isn't some abstract physics thing. You have felt inertia your entire life. Ever been on a bus when the driver slams on the brakes? The bus stops, but your body wants to keep going forward because of inertia. That's why you lurch. Same thing when it takes off. The bus moves, but your body wants to stay put, so you feel like you're thrown backward. Inertia is the whole reason we need seatbelts. So, does a feather have the same amount of this laziness as a bowling ball? Nope, not even close. The amount of inertia an object has is measured by its mass. It's really simple. More mass, more inertia. Let me put it this way. What's harder to get moving from a dead stop? A bicycle or a freight train? And once they're moving, which is harder to stop? The train, right? Of course, because it has so much more mass, it has way more inertia. It puts up a much, much bigger fight against any change to its motion. Okay, so the first law tells us what happens when everything is balanced and there's no net force. But what happens when there is a force? What happens when you actually decide to push that bicycle or try to stop that train? Well, that's where Newton's second law comes in. But first, we need to introduce a new character, momentum. All momentum is an object's mass times its velocity. You can think of it as mass in motion. A tiny but super fast bullet has a ton of momentum. A huge, slow-moving ship also has a ton of momentum. It's the quantity of motion an object has packed inside it. So what's the connection between force and momentum? It's actually pretty direct. A force is what changes momentum. If you want to change how an object is moving, speed it up, slow it down, change its direction, you have to apply a force. That's all this fancy-sounding law is really saying. And luckily for us, all that formal language can be boiled down into one of the most famous and powerful equations in all of science. F equals ma. Force equals mass times acceleration. You want to make a mass accelerate? You need to apply a force. It's that simple. So what does F equals ma actually tell us in the real world? It tells us the force you need depends on two things: how heavy something is and how quickly you want to change its speed. As you can see here, getting a lighter object to accelerate really fast can actually take more force than getting a heavier object to accelerate just a little bit. It's a balancing act between mass and acceleration. And here is a perfect real-world example. Why do you see a cricket fielder or a baseball catcher pull their hands back as the ball comes in? They're using the second law even if they don't know it. By pulling their hands back, they increase the time it takes to bring the ball to a stop. A longer time means a smaller deceleration, which, thanks to F equals ma, means a much smaller impact force on their hands. It's the difference between a clean catch and a broken thumb. Okay, so we know what happens with no force and we know what happens with a force. But there's one last piece of this puzzle, and it's a big one. Newton realized that forces are never lonely. They never, ever exist by themselves. They always come in pairs. Now, this is probably the most famous of the three laws, but it's also the one that gets misunderstood the most. All it means is that if object A pushes on object B, then object B is pushing back on object A with the exact same amount of force, just in the opposite direction. Let's look at a few examples. When you walk, your foot pushes backward on the ground. That's the action. At the very same instant, the ground pushes forward on your foot. That's the reaction, and it's literally what moves you forward. Or think about a gun firing. The gun pushes the bullet forward, and the bullet pushes the gun backward. That's recoil. Now, this is the most important part, the bit that trips people up. You might be thinking, wait, if the forces are equal and opposite, shouldn't they just cancel out and nothing moves? And the key is that the action and reaction forces are acting on two different objects. Your push acts on the road. The road's push acts on you. They can't cancel each other out because they aren't even acting on the same thing. So let's bring it all together now. These three laws aren't just separate rules for a physics exam. They're a complete package deal for understanding pretty much all motion everywhere. And it's how they all work together that's so amazing. Law 1 sets the baseline. Objects are lazy. They resist change. Law 2 gives us the math. It's the recipe for how to create change with the force. And Law 3 is the great cosmic rule that reminds us that every push is also a pull. It's always a two-way street. From the way you feel in a car taking a sharp turn to the simple act of walking across a room, these three laws are running the show behind the scenes. They are simple, they are elegant, and they are powerful. They are the rules the universe plays by. So the only question left is, now that you know the rules, what are you going to see differently?